Hello everyone, I'm Yao Yao. I will talk about our work, Adaptive Aggregation Networks for Class-Incremental Learning. It is joint work with Born and Qianru. Class-incremental learning aims to learn new data by incrementally updating a model trained on previous data. In the first phase, we train the classifier using data 1, and we evaluate this classifier on the corresponding test set. In the second phase, due to the memory limitation, we cannot keep all samples in data 1. We select example 1 from data 1 and we get data 2. We update the classifier and conduct the evaluation on all concepts the classifier has learned so far, which is the standard setting. The same applies to the third phase and so on and so forth. The main challenge for class-incremental learning is stability-plasticity dilemma. Higher stability weakens the model from learning the data of new classes, and higher plasticity results in forgetting of the old classes, that is, catastrophic forgetting. How to address the stability-plasticity dilemma? Existing methods try to address this issue in the following two directions. Regularization-based methods try to design regularization terms to consolidate previous knowledge when learning new data. However, they don't perform well with long sequences. Replay-based methods try to select or generate better examples to recall the old knowledge. However, they make the model overfit the examples. Our method is Adaptive Aggregation Networks, that is, AANets. We try to design a novel network architecture where we maintain two types of blocks, stable blocks and plastic blocks. The benefits of our AANets are as follows. First, our method works well on long sequences. Second, our method relieves the overfitting problem. Third, our method is generic and can be combined with regularization-based and replay-based methods. Our AANets consist of the following components. First, plastic blocks. We update all the parameters for the plastic blocks. Second, stable blocks. We freeze some parameters of the stable blocks and update the others. Third, aggregation weights. We use these weights to aggregate the feature maps from the plastic and stable blocks. The plastic and stable blocks provide the candidates for different network architectures, and the aggregation weights are used to balance two architectures. We train different components of AANets using different data. The plastic and stable blocks learn the knowledge from samples, so we use all available data to train them. The aggregation weights are used to balance two types of blocks, so we train them with the balanced subset. We can apply different aggregation weights for different blocks in ResNet and get the adaptive aggregation ResNet. This table shows the ablation results. Comparing row 3 to row 2, we can see the effectiveness of using two types of blocks. Comparing row 5 to row 3, we can conclude that meta-learning the aggregation weights boosts the performance. Comparing row 5 to row 4, we can observe learning the aggregation weights on balanced subset achieves further improvements. In this table, we can observe that compared to the state-of-the-art, our method improves the accuracy significantly. In this Grad-CAM visualization, we can see that our AANet benefit from both plastic and stable blocks and perform well in all phases. For more details, you can visit the project website. We have released the code on GitHub. Thank you for listening, and we are happy to answer any questions.